Okay, so our first common ion problem. We're going to use PbI2, lead 2 iodide. PbI2 has a KSP of 9.8 times 10 to the minus 9. And we're going to do some calculating, but now we're going to have a common ion present. So we're going to calculate the concentration of Pb2 plus in a saturated solution of PbI2 that's been prepared in 0.10 molar Ki. Now what that does for us is it puts a 10th molar iodide already in the solution. And that 10th molar iodide feeds into our equilibrium because there can be only one concentration of iodide in solution. We don't have 0.1 molar from this and then whatever else we get from the other one kept separate. There's one iodide concentration. So we set up our PbI2 equilibrium. Same kind of thing we've seen before. But now when we set up our ice table underneath it, our initial conditions, we don't worry about PbI2, there's no Pb2 plus yet, but there's 0.10 molar iodide already present. So at the change condition, we have to shift to the right. We got a bunch of solid over here, got to shift to the right because there's no Pb2 plus yet. So we have plus X amount of PbI2 and plus 2X amount of I minus. The 2 because of the 2 up here in the coefficient. So at equilibrium, still not worried about PbI2. We have X amount of Pb2 plus and 0.10 plus 2X amount of iodide. Okay, now, if you're thinking what I'm thinking, when we get to this stage, we're going to have a messy equation here when we plug in our algebra. If we can't drop this 2x like we did back in the acid chapter and back in the regular KC chapter. So we do the same thing here. We compare this 2x that's associated with the 0.1. Okay, the 0.1 is much, much larger than KSP. So when that was the case back in the regular equilibrium chapter, we could drop that 2x. Same thing happens here. Because 0.1 is much, much larger, our factor of 100 difference, remember that we went with? We can drop that x, which simplifies everything, just like it did back then. It just didn't look like it was going to simplify it when we were plugging them in. So KSP is equal to Pb2 plus times I minus squared, which has a numeric value of 9.8 times 10 to the minus 9th. And we plug in our algebra numbers. So we have x and 0.10 squared as our left-hand side equals 9.8 times 10 to the minus 9th. So x is equal to 9.8 times 10 to the minus 9th over 0.10 squared. So x has a value don't forget to square the 0.1. 9.8 times 10 to the minus 7th. So our value of 9.8 times 10 to the minus 7, that is the molar concentration of Pb2 plus, because Pb2 plus is X. So this happens to be our answer. So that's the molar solubility of Pb2 plus from lead 2 iodide at regular conditions. So let's do this without the common ion. So if we work this as a regular problem, what is the concentration of Pb2 plus and saturated PbI2? So we still have our KSP, 9.8 times 10 to the minus 9th. And from PbI2, Pb is x, I2 is 2x. So KSP is equal to x and 2x squared equals 9.8 times 10 to the minus 9th. And so 4x cubed, as we simplify that side, x cubed is equal to 9.8 times 10 to the minus 9th over 4. That was 2.2. 9.8 times 10 to the minus 9 divided by 4. 2.45 times 10 to the minus 9. So x is the cube root of that. So y to the x to the 1/3 power. 1.35 times 10 to the minus 3rd. And from our problem setup, PB2 plus is x still. So now I want us to compare this number without any iodide already present. 1.35 times 10 to the minus 3rd to our concentration when we had 0.1 molar iodide present. There's a factor of at least 1,000 difference there. The iodide suppresses the solubility because notice we're adding a product here, right? When you add a product, you shift equilibrium to the left. That means less Pb2 plus dissolves because you've already got some product present. And that's the common ion effect. Anytime you dissolve a slightly soluble salt in a solution that already has some of one of those ions present, it will decrease the molar solubility of the substance as well as the concentration of the ion that you're adding to the solution fresh. Okay? Thanks for paying attention, guys.